population is the number of organisms of the same species in a given place and a given time. So if we understand what a population is, what we're interested in this particular video is how populations change over time and what causes that change to happen. So we're going to have a look at typical population dynamics and describe them. And then we're going to explain how population sizes are regulated and what kind of factors can impact upon that. So a little bit about population dynamics. Population dynamics is about how populations change over time. Populations are never static. They can go up, they can go down, they can remain relatively stable, but there will always be changes in that particular sense. The most obvious way in which population dynamics can change is an increase, and this is seen in what is observed here. This is something called exponential growth, and this tends to happen if you were to, say, introduce a new species into an ecosystem and it did well, it would begin to reproduce. So in this case, a bunny or a rabbit, and the rabbits reproduce. And over time, as they reproduce, their growth increases exponentially, and this is called a J-shaped graph. This is something that you would observe in an ecosystem whereby which resources are completely available. There is no limit. The key thing to note about this particular type of growth is that it's very unrealistic. It's very unrealistic that exponential growth can continue forever. We can see exponential growth in a number of different places. If we look at, for example, the human population since the Industrial Revolution, the growth of the human population has been exponential. And a lot of experts suggest that this isn't going to carry on for much longer. We can't sustain that level of population growth. We also see it in bacteria. Bacteria growth on an agar plate or a petri dish, exponential. But again, there's going to be a limit to this. And what we tend to find is that actually population growth looks a little bit more like this. From a starting point, we get an S-shaped curve instead. Population growth starts slow, and that's what we call essentially the lag phase, which is just at the beginning. It then starts to increase, and we get a log phase, which is this steep line in the middle, and then we get a plateau. And this is much more realistic of what we would expect a population to go through from a small starting point. And there may be various reasons. We'll talk about various reasons as to why we might see this population growth kind of happen. What we tend to find then is that population size will plateau at what we call a carrying capacity. And carrying capacity is not a set number. Okay, so the carrying capacity is the rough number of individual organisms that an ecosystem can support for a given species, essentially. And this will depend on a number of things. It will depend perhaps on food availability, how many predators are around, and all these sorts of things that we'll consider a little bit further into the video. But what we need to realize is that this is much more representative of the way populations change over time, especially from small numbers at the start of time. Okay, so this might be a colonization event where you get a new species introduced to an island or an area. An invasive species, for example, may change like this, or it could be after the result of a population decline due to hunting or a disease or something. We'll talk about that in a minute as well. Now, this can be represented in real life data. So this is data for the number of seals in an area in America where hunting was up to around 1975 encouraged by the government because seals were seen as a predator that were feeding on fisheries. Hunting was banned around this kind of time, and ecologists began to count the number of seals. And what they saw was this particular graph here, and what you can see again is a gradual increase to start with, up to around 1980, where the increase is much more exponential. And then from around the mid 80s, you start to get a plateau into the 1990s, and it plateaus at around 7,500 seals. And we see a slight drop here, and that may be to do with various reasons as to why that is. But what we have been able to tell from this particular graph is that the rough carrying capacity for this particular habitat and ecosystem is about 7,500 seals. And that will change depending on the factors that are available. We can see this in real life data, this S-shaped curve that's really important. And it's essentially what we call a logistic curve. Okay, and the key word there is log. It's a log graph essentially, and that's what an S-shaped curve means. So what we want to think about then is what's actually regulating population. So how is population regulated? Now, to understand this, what we need to understand is that population change is a result of 4 key factors, essentially. 2 of them are positive, births and immigration. So births and immigration increase the population. So if births go up, then the population can go up. And immigration is a process by which organisms move into an ecosystem. So we take all the births and all the immigration and we minus away the negatives, the deaths and the emigration. So deaths is where obviously things die through predation or through disease or through natural causes. And the emigration is where the individual organisms leave the area. And what this gives us overall over a given time span is a population change. So population can either go up or down or stay relatively stable over time. And we might, as ecologists, measure population on a regular basis in order to plot population change over time. Now, what we need to realize at this point is population is regulated in 2 key ways. Okay, so the first is biotic and the second is abiotic. So biotic means anything that regulates the population size that is also a living thing. And abiotic means anything that is non-living, kind of impacting upon this. So biotic regulation, there's some really famous case studies around this. The first is based around predation and competition, and this is shown in this particular graph here. And then the second is disease, and this is shown in this graph here. Now let's look at these graphs in a bit more detail. The predator-prey interaction model, and this is a very famous model, and it often uses a lynx and a hare. In this case, it's using rabbits and a wolf. It's kind of similar. And you can see the 2 lines that represent the 2 populations. What's really important here is that you can see both populations fluctuate. They go up and they go down. And you should be able to make out the S-shaped graph in each case. So it starts down at the bottom, it goes up exponentially, and then it plateaus off before falling. Now what we're going to think about here is what causes the blue line to drop? Well, the blue line drops to start with because of an increase in the predators. So as the predator population increases, more of the rabbits are dying than are being born. So the blue line drops. Now as the blue line drops, the red line actually continues to increase. And the red line actually peaks at a point at which the blue line is kind of halfway through its fall. Now at this point, competition comes into play. So the wolves are beginning to have to compete for a smaller number of rabbits. And what this means is that some of the wolves are going to lose out. In fact, what we probably considered in the last video is that competition is negative for all involved. So the population of the wolves begins to decline, and it declines along with the rabbit population for a short period of time. And as the number of wolves drops, the amount of predation begins to drop, and therefore the rabbit population, rather than going extinct, is able to begin to bounce back. And as it bounces back, it goes back into an exponential growth, and we get another log curve. It goes up and it plateaus, and you get this going on and on and on over and over. And going back a couple of lessons, some of you might remember we talked about lions and zebras kind of requiring each other. And the dependence of the lion on the zebra is fairly obvious. You know, the lion eats the zebra. What we perhaps don't consider is the fact that the zebra population actually requires the lions to keep the population in check. And this is the case with any kind of predator-prey interaction. And it'll be the same with these rabbits and wolves, is that essentially the wolves and the lions and the apex predators will pick off the weak prey first, and they keep the population stronger for that reason. So they'll pick off any diseased individuals, they'll pick off the weak, and essentially that keeps the population strong. So where you see the rabbit populations dropping, the ones that remain are the strongest, the fittest individuals in that population, and they produce a stronger population that bounces back, and that just continues over time. So predator-prey interaction models are really important in terms of the strength of ecosystems. Now, the other one we consider then is disease. Disease is known as a bottleneck event, and this occurs when you may, in this particular case, you have a population size that's fairly static. You see slight fluctuations and it's going slightly down, slightly up, but not a lot away from carrying capacity. And then we get a bottleneck event. In this particular case, this is a disease hitting a population, a natural population, and that population drops quite dramatically. There's two possible options as to what can happen to this particular population at this point. Now, it can become extinct, and this could be through weakness in the population, lack of genetic diversity, or things like that. That could cause that population to become extinct. But in most cases, population will recover, and it recovers. Then what we'll see at the recovery stages, we'll see another S-shaped bend, essentially, that gives us that kind of slow increase and then an exponential increase up to a carrying capacity. A bottleneck event could also include perhaps the introduction of hunting or poaching at a high level that causes a rapid decrease in a population size. And it's really important that ecologists study these things so that we understand how to conserve populations over time. Do we need to step in? Do we not? And it really informs those kind of decisions to be made. Now, abiotic regulation is where abiotic factors impact upon population size. And there's three really good examples here. And what we need to realize is that these three don't discriminate. They don't necessarily pick off the weakest, although drought might do, famine might do, but they can kill indiscriminately within a population. So it doesn't really pick off the weak like the predators do. But drought and famine, where there's a lack of water and food. Fires and disasters. So fires are quite important in certain habitats, as we looked at in the biome area when we looked at the grasslands. They're predominantly seen as places where fires happen on a yearly basis, and that keeps trees from growing. But that can also impact upon population sizes, and you might get bottleneck events caused by big fires. Alternatively, animals might choose to migrate away from those fires and come back at a late stage, so that causes population change. And extreme weather, so storms and tornadoes and hurricanes and all these sorts of things that can kill individual organisms indiscriminately again, and can have bottleneck effects on a population, which can then lead to that increase that you might see. So in summary, we understand that population is the number of individuals of one species in a given place and a given time. Population changes over time. We call that population dynamics, and change can be exponential if no limiting factors exist. What we need to understand is that this is rare, so we do not tend to find complete exponential growth forever. Logistic population growth, and this is where you see the S-shaped curve, plateaus at carrying capacity. And carrying capacity is essentially the number of organisms that an ecosystem can sustain over a period of time. And populations are regulated by biotic and abiotic factors. Now that you've had a watch of this, have a go at the quiz. Good luck.